gives you time. Okay.
Go. Hi, Ty.
Hi, Ty.
Hi, Ty.
Hi, Ty. What are we doing?
You're my best friend.
We
Good.
say hi to whoever's absent
He's not
every screencast.
He's on screen.
No, she's
Ty, he's serious right now. Yeah.
Not right now. It's not live. But if he were to watch this back.
recording live from Toledo period.
Wait, is that what it means? Wait, the screencast on our, that's our class?
Yeah, it shows that.
I
It
thought it
shows.
was random YouTube videos.
No, it shows what's on the board. It shows what's on the board with us, all of our voices.
Yes, I just post random YouTube videos, Emma.
That makes my life so much easier, thank you.
I don't always remember, but if you email me ahead of time if you're sick or something, if you're sick or if you're gone for a field trip or you're visiting a college, just email me and I can do the screencast. It's easy. It's just a click of the button.
Can you do it for the rest of me?
Okay.
I won't be here.
Okay, so let's review. And have your you'll want to have your calculators handy.
How?
So this is something that we covered on Friday. No, not on Friday. Whenever I saw you last. It was a long time ago. Wednesday. So how might the derivative fail to exist? Okay, so remember this f prime of a means the derivative, which is the slope of the tangent. So when we have a corner, which means from the left and the right, they have they have different slopes. That's one example. We have a cusp. This is if we look at the tangents, and as you get closer and closer, they approach. This one approaches a negative infinity. This side approaches a positive infinity slope.
Do that by looking or by like using points?
This is something specific in terms of a rational exponent when you have even over odd, where the even power is smaller than the odd,
Then you get a cusp.
you get a cusp.
Good, I got that right in the homework.
So if you had like 4/5 would be an example of a cusp also. A vertical tangent is cube root or fifth root, okay, an odd root. This is going to give us a tangent as you approach 0 from the left and right. It approaches infinity or negative infinity.
Does that also equal x to the 1/3?
X to the 1/3 is the same as the cube root of x.
So then,
So if I had written x to the 1/3, that would be a vertical tangent.
But that's autumn for all.
oh, it has to be
Even over odd.
Oh.
Okay, discontinuity. Discontinuity, you can't look at a point of tangency if they don't even match up. If it's not a continuous function, there is no tangent right there. Okay, so we went through this example here where we showed that from the left, the derivative was 2, from the right it was -1, therefore it's a corner. Okay? Yes, Natalie? Yeah, the whole quiz is calculator, okay.
Best news I've heard all day.
All right, then we talked about you take any function and you zoom in. We zoom in further and further, or closer and closer, and the more we zoom in, the more it's going to look like a straight line. And that's basically what we're looking at with a tangent line. So if we were to zoom in and zoom in and zoom in, it's going to start looking like a tangent line. That's what happens in those cases. Okay, we talked to also, there were 3 different ways that we found the derivative on our calculator.
And that's different than finding is the derivative finding this the same as finding the point of differentiability?
That is different. Okay, the derivative is, we're basically saying that is the slope of the tangent at a particular point. Now,
Which is also the same as the instantaneous.
one way that you could tell if it came out, like let's say you weren't sure if it was differentiable and you went through this process on your calculator, it would come up with an error. Like if there was no derivative, it would say error on your calculator. Okay. Okay, so we have differentiability implies continuity. So if we know it has a derivative, then it has to be continuous. Note that the converse of that is not true. Okay, converse is not true. Therefore, if it's continuous, it doesn't necessarily mean it's going to be differentiable. Remember those examples that we just looked at? It could be a corner, a cusp, or a vertical tangent. Those are all continuous. Like an absolute value function, for example, looks like a V. It's continuous, but it's not differentiable right at...
Differential means it has a slope for every.
Right, differentiable means it has to have the same slope from the left and the right. And it has to be a real value. Okay, so here we have our example. The graph of a function over a closed interval D is given. At what domain points does the function appear to be differentiable? And then B is continuous but not differentiable, and C is neither continuous nor differentiable. Not differentiable, nor, well. Okay, so the first part, where does it appear to be differentiable, Natalie?
Differential?
Yeah.
About like one, I would say from 0 to 3.
Okay,
Or you could actually do from -2 to 3 except.
let's just take the word differentiable. What does that mean again? It means that it, okay, same slope from the left and the right. So anywhere there's a corner, and in this case there's no cusps or vertical tangents. So basically anywhere there's a corner or a discontinuity, it's not differentiable. So we want everything else. Emma?
Just what's the definition of a cusp?
From the slope from the left is negative or positive infinity, and then from the right it would be the opposite. So the example that we did from the left, it was approaching a slope of negative infinity, and then from the right it was approaching a slope of positive infinity. Okay, so differentiable. We're going to include, since this endpoint right here is colored in, we're going to use a bracket. So from -2 to -1. Yeah, now some books will use parentheses and brackets. We'll stick with parentheses for now. Now, I can't include -1 because there is a corner right there. Do you see that? So union, we'll pick it back up at -1, and then we'll go to 0, but we'll use parentheses around 0 because that's an open circle.
And
Then what?
then our union bracket 0.
Okay.
Is it 0?
Now, we'll,
Oh no, wait.
yeah, we'll just say from 0, since it was a discontinuity there. Technically, this first bracket, where I put -2, most books will be fine with using parentheses around there. That's fine.
I'll use bracket.
It's bracket or parentheses is fine. So then 0 to 2, and then 2 to 3.
A lot.
Right, so all of those places it's differentiable. Basically the numbers we've excluded would be the corners and the discontinuities. So where is it continuous but not differentiable? I pointed it out
-1
at -1.
and 2.
Are you sure about that?
No.
Is it continuous at 1? Or sorry, is it continuous at 2?
No.
Yes.
There's a removable discontinuity here.
Oh, right.
It's not
So it's I lied.
Continuous at 0 or
C.
Okay. C, where is it neither continuous nor differentiable?
0 and 2.
Good. Okay. I think you had some homework problems similar to that.
Yeah.
Okay,
They're
so
a lot
how-
easier than that.
But you didn't have to do the brackets. It was like 1 point of discontinuity, so you could say
Oh, I see.
from -infinity
I did a
to
bracket.
infinity except for.
I see.
Well,
I like putting it
originally-
in interval notation because that's how I'm going to ask for it. I'll ask you for where are the intervals that it's differentiable.
Well, I originally did that. It was just a line with one of them was just like a straight line, and I originally put infinity to infinity, but then I changed it from like within the domain, so from -3 to 2 does not matter.
Yeah, that should be fine.
Yeah.
Okay. The function fails to be differentiable at 0.
That was my
So
homework.
determine whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. You can use your calculator for a problem like this. So if we want to look at, we'll do x to the, oops. Sorry. You think it's a cusp?
Yes. It's odd, even though it's odd.
Even over odd? Okay. So do you see how it kind of curves in? Okay, when it has that kind of effect, that is definitely going to be our cusp. And 1 over x, what's that? What do you think?
Vertical tangent. Yeah. An odd. Yeah, it's an asymptote.
Ah, it's an asymptote there. So that has to be a discontinuity. That's an infinite discontinuity, right? At 0? Ah, okay, hold on a sec. Be careful here. The graph itself has a vertical tangent.
That's annoying.
But the vertical tangent means that it's a discontinuity.
So it doesn't matter what kind of discontinuity it is as long as it's a discontinuity.
Right, it doesn't matter.
It's an infinite discontinuity, but it's a discontinuity.
Right, this would be, if I asked you to describe what kind, you would say this is infinite. In order for it to have a vertical tangent, it has to be continuous.
A whole lot of factor.
Okay, our example, the vertical tangent was the cube root of x. That's pretty much the only kind that we would have, an odd root of x would give us a vertical tangent.
Yeah,
Okay, nothing else is really going to give us that vertical tangent. It's a little confusing because this is an asymptote, so it doesn't actually have a value at 0. So that's the discontinuity. Okay, find all values of x for which the function is differentiable. So I'm looking for intervals here.
That's what I did. There's some of these on homework. I didn't get that.
Okay, where you could graph this, but what I would just look at in the first one, it's a rational function. So consider where the denominator is undefined are going to be discontinuities. So just looking at,
That's a thing. Can we graph that?
oops, you could graph it. Sorry, that's supposed to be,
So it's not it's not differentiable though, right?
right, it's not differentiable where this would be equal to 0. So basically we can't have -1 and +1. So I can have everything else. So it's -infinity to -1, -1 to 1, 1 to infinity. You could,
But is there anything else in this case or not?
so rational function, there should be nothing else going on with a rational function. Rational functions should only have discontinuities, basically. That's what you're going to be looking for. You could have a corner. I mean, if it was part of a piecewise function, but it's just a straightforward, you have a polynomial in the numerator, polynomial in the denominator, so you're really just looking for where the denominator is 0.
Doesn't the numerator cancel with the denominator?
Ah, so if you look at x cubed minus 1, you could actually factor out an x minus 1. That just means that x minus 1 would give us a removable discontinuity, but it's still a discontinuity, so I don't care about what's going on in the numerator at all. So just make it easy for yourself. Just look at, if you have a rational function, just look at the denominator.
So did we say equal to 0, the whole thing equals 0, and you got it?
Yep.
That's a lot easier.
Okay, how about the next one? So I see a cube root. Basically, if I set what's inside the cube root equal to 0, that's going to give us, remember what did cube roots give us? Those were vertical tangents.
Yeah.
So if I set x minus 2 equal to 0, basically, we're saying x can't be equal to 2. And that's where it's, that right at x equals 2 is going to give us that vertical tangent.
We could just pull, okay, yeah.
So it's going to just be -infinity to 2, and then to to infinity. Because that's where it's going to switch. Remember, the cube root looks like that S shape. So whatever the horizontal shift will be, that's where your vertical tangent will be located. Make sense?
That's for any odd
Cube root, odd root.
odd root, and for even roots, it just has to be greater than 0.
Right. So even root, it's differentiable over its domain. So for example, if it's just like square root of x minus 2, then it would just be differentiable from 2 to infinity, including 2. That doesn't have a vertical tangent or cusp or anything. It's just not defined for negative values. So we would just say it's differentiable on its domain. Which in part A, that's actually the case. So in A, this is the domain here. Whereas over here, what's the domain for B? It's all reals, right? It's negative infinity to infinity. So you just have to consider where that vertical tangent would be. Does that make sense? Okay. I think this is the last thing, right? Yeah. Okay, we did an intermediate value theorem. Did we do the intermediate value theorem
Yeah.
already? Where we said if you had like an A and then a B, then it has to take on all Y values in between. Does that sound familiar?
Yeah.
It was a while ago. I think it was, usually you learn it in pre-calculus somewhere.
No, didn't you just say for limits or something?
Yeah, but it's part of usually you learn it in part of pre-calc also.
No.
Like where it crosses the
It's gonna
x-axis.
stop hanging out.
Okay, well, okay. Intermediate value theorem for derivatives. It's basically just saying if you have, let's say here's A, okay, so here's, picture you have a tangent here. Here's f prime of A is your slope. And then, I don't know, we'll pick B here. So f prime of B would be that slope. Now, there's not that many differing slopes in between there, but you see how it's kind of getting steeper? So all values in between there have to exist. Like basically, the slope can't automatically jump from here to here. It's got to gradually get to that slope. If it was a jump, then it wouldn't be differentiable. Intermediate value theorem. Remember, intermediate value theorem has to be differentiable, so there can't be any discontinuities. There can't be a corner, a cusp, or a vertical tangent. It's got to be a smooth curve. So that means, like, let's say my slope here is 1, and here my slope is 2, then somewhere in between there I have to have a slope of 3 halves.
One more time.
Okay, let's say my slope, just as an example, let's say my slope was 1 here, and let's say here my slope was 2. So that means somewhere in between A and B, there has to be a slope of 3 halves.
How would we get 3 halves?
I just picked a number between 1 and 2.
Okay.
So
Okay.
there have basically all the values between 1 and 2. There
Okay,
has to
so
be a
every
slope of those values.
Okay, so every value between 1 and 2 will be accounted for.
Exactly. It can't skip over anything.
Got it.
It's got to be a smooth, continuous curve, and so it can't jump from a slope of 1 to a slope of 2, otherwise that would be a corner. So it has to take on all the values in between. That's intermediate value theorem.
Do you understand?
Yes.
Let's hope so.
Yes.
We'll get an answer on